I think my business partner is blowing everything out of proportion. He's single-handedly ruining my balloon animal business. You get it? Blowing up. Anyways, so speaking of proportions, we will be looking at the behavior of sample proportions today. So we'll want to describe the shape, center, and spread, and actually we're also going to calculate some probability. So proportions are typically used for categorical data to determine the percent that fall into a certain category. This should sound a lot like a binomial distribution, where n is the number of attempts, or in our case, how big our sample size, and x are the number that fall into that category. So x, let's say yes, or something like that. The probability of success, or I should really say the proportion of success, is p, just like before. All right. So let's revisit AP scores, because being an AP teacher, I find them interesting. In 2018, 60.2% of 203,855 students scored a 3 or higher on the AP statistics test. So what I'm going to do is pretend like we're going to sample from this population and look at what percentage we would expect to say that they scored a 3 or higher, which is technically passing the AP test. So we'll look at how it would behave for samples of 10, 20, and 40. And if you go to this applet that I have here that's listed on your notes, GeoGebra has a beautiful little binomial distribution applet, and it shows you the shape and everything, very easy to use. So I went ahead and entered in n is 10, and the proportion in this case is 0.602 because it's 60.2%. And this is the distribution it created. So the center is at 6.02. All right, that's assuming, it actually would probably be very close to 6, but it's about 6.02 would be the expected value. Then the shape, it's very symmetric, looking a little bit, not quite like a normal distribution because you can see some gaps here, but it's close. And then the variability, well, we can just calculate that either using square root of NPQ or using the binomial distribution. They both work, and I get 1.5479. Okay, so let's go ahead and double our sample size. What happens to the mean? Well, we expect twice as many people to be passing in a sample of 20 than we do in a sample of 10. The shape is even more symmetric, and the variability is going to actually be a little bit bigger. Now, you might say, wait a second, the spread looks smaller on here. Well, relatively speaking, I would agree with you, and that's an important point. But absolutely, on an absolute basis, the spread from here to here is larger than the spread from here to here. So the spread here is 2.189. Finally, we have a sample size of 40. And here we would expect even twice as many as last time. So we have about 24.08 is the average we would expect would be passing the AP stats test in a sample of 40. It's very symmetric now, looking much more, still not perfect, but looking a lot more like a bell curve or a normal distribution. And the variability, even though it looks even tighter than the ones above, it is slightly larger on an absolute basis. And we'll get to that in a little bit. So the average, here's our table, and I entered all those values in for you. Now, the expected value for the proportion, let's go ahead and divide the expected number who will pass divided by n, and that would give me the proportion, 0.602. Let me go ahead and do it here and here. Well, does it make sense that 60.2% would pass if that's what we kind of told it would do? Of course. So for proportions, the expected value does not change. Why is that? For the proportion value? Well, the mean of the proportion is just going to be the regular mean divided by the sample size. But for binomial distributions, the mean is going to be n times p. So those two n's simplify, and you just end up with p, the proportion. So the mean proportion is the proportion. So in this case, if I tell you it's 60.2%, it's 0.602. Now let's take a look at the standard deviation for the proportion. If I go ahead and divide this value, that standard deviation, by 10, I get 0.1548. Okay. Let's go ahead and divide the next one by 20, 0.1095. And then the last one by 40, 0.0774. So what we're noticing is that actually it kind of shows in the picture that the proportional standard deviation is tightening up with larger sample sizes, and that kind of makes sense based on the shapes you saw. So where's this coming from? Well, we know standard deviation for a binomial distribution is square root of n times p times 1 minus p, all right? But I'm going to go ahead and divide that by n, like that, okay? And I'm going to go ahead and square that n on the bottom there so I can put a square root on it. So square root of n squared is just n. Those two are the same thing. Since I have a square root over a square root, I can combine them into one fraction. And then you'll see that this, and that's one of these n's down here, simplify. So we just end up with this formula. So the standard deviation for proportion is p, square root of p times 1 minus p, divided by n. So if the proportion's the same, as I get bigger and bigger sample sizes, what's going to happen? It gets smaller. Not by n, but by the square root of n. So if you notice, my standard deviation here for n is 40 is twice as small, or half as big, as my standard deviation for 10. Well, a sample of 40 is 4 times bigger than a sample of 10. What's the square root of 4? 2. So that is the kind of the scale factor going from between these two. This one is twice as big as that one. Okay, so what are some of the conditions that we can use a normal distribution for? Well, or binomial even. Well, there's the 10% condition. When do we check it and why do we need it? Well, Bernoulli trials are defined as trials that are independent and the probability p is unchanging. If I start taking more than 10% of the sample out and keep going, then my proportions are going to change. I mean, they might not, but they could very easily change. And if we sample without replacement, which is basically how we do it. Now, if we were replacing it, it wouldn't matter. But we're not replacing normally in samples. So that means the probability will change as we get past 10%. And the closer our sample size is to the population size, believe it or not, the less variability we're going to get. It's harder to change an average when you have 20 grades in than if you have 4. So the more that we have, the less variability we're going to have. All right. So the standard deviation that we get from that formula, square root of n times p times 1 minus p, is actually going to overestimate the variability. So this must be checked when using both the binomial distribution and the normal distribution. So let's look at sampling distributions for different values of p and n. I do have a typo here. That's supposed to be 0.9. So first of all, the center here should be 0.1. The shape is skewed to the right. Why is that? Well, my sample size is only 20. And if I remember that n times p for the binomial distribution, I only get 2, and it's supposed to be 10 or higher. Variability, I just use the formula for a proportion, it's 0.0678. Let's go ahead and take a bigger sample size, 10 times bigger, of 200. The center is still the same. The shape is now symmetric because my sample size is big enough to satisfy the n times p rule. The variability is actually about 3 times smaller. Not exactly 3 times smaller. But if you were to say, how much bigger is this sample here compared to that? It's 10 times bigger. Square root of 10 is a little over 3. So this one is a little over 3 times bigger than my less variable example with my larger sample size. Okay, now let's look with 0.5. and a sample size of 20. Well, the center is 0.5. The shape is pretty symmetric because in this case we actually hit that NP rule. And then the variability using the formula is 0.118. Well, my center is going to stay the same. My shape is even more beautifully symmetric. I would expect my variability to be a little bit more than 3 times smaller, and it is. All right. And finally, let's go with an extremely high value of p of 0.9. That's what it really is, by the way. The shape is skewed to the left because we didn't fit that 1 minus p times n rule. That one also has to be greater than 10. So we have to be more than 10 away on the expected value from the edge of our range. And the variability, just using the formula, oh, look at that. Those two match. Why is that? Oh, well, because 1 minus p is 0.9 over here, and 1 minus p is 0.1 over here. It's the same product and the same sample size. Okay, now we look at a sample of 200, 10 times bigger. Center stays the same. Shape is even more symmetric. That used to be skewed, but now we've gotten enough of that NP and that n times 1 minus p rule. So we're far enough away. And the variability is about 3 times smaller because the sample size is about 10 times bigger. Square root of 10 is a little over 3. So for large enough values of n, the variability is smaller and the distributions are symmetric, regardless of the value of p. Which brings us back to the large counts condition that I was referring to. That is that n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. The large counts, what that refers to is large enough number of expected successes, that's n times p, and expected failures, that's n times 1 minus p. We saw that when the counts of success, n times p, or the counts of failures, n times 1 minus p, were not greater than or equal to 10, the distributions were skewed. If we're only using the binomial distribution, that's fine because it'll actually do all the math for you. But if we're trying to approximate to the normal distribution, which assumes that it has to be symmetric, then we've got an issue. And especially later, we haven't covered it yet, we'll be calculating confidence intervals and performing hypothesis tests, which heavily rely on a normal distribution. So let's take a look at an example. According to the U.S. News and World Report, in the population of 4,361 students enrolled in Penn State World Campus bachelor's degree programs, 811 have military experience. We're going to take a sample of 100 randomly selected students. So what is the mean of the sampling distribution of p hat? I should say that p hat is the proportion of students that have military experience. Well, we know that n is going to be 100, but we're not going to need that just yet, okay? My mean is going to be the 811 over 4361, or 0.1860, okay? So I would expect my sample to come up close to that. There'll be some variability, and we'll talk about that. Calculate and interpret the standard deviation of that sampling distribution. Well, I'm going to use my formula, square root of q. Remember, sometimes I use q. That's also known as 1 minus p. And that's 0.186 times 0.814 over 100 and take the square root. So it's about 0.0389. Now, I need to check the 10% condition. Well, 100 is less than 10% of my population, 4,361 students, so I'm good. So how do we interpret the standard deviation? In simple random samples of size 100, the sample proportion of students with military experience will typically vary about 0.0389 from the true proportion of 0.1860. Can we say that this distribution is approximately normal? That's where we have to check the large counts. And we already know our 10% condition is met. So because my successes, 18.6 is greater than or equal to 10, and my failures, 81.4, are greater than or equal to 10, I can say that the sampling distribution is approximately normal. So we can use binomial distributions to calculate probabilities, and those work. For large sample sizes, it is usually easier to use the normal approximation. So what is a probability that less than 10% would have military experience in a random sample of 100 students? Well, the nice thing is, let's see, I know the mean is 0.1860, and sigma p hat is 0.0389. I am trying to find the probability that my sample might give me a result less than 10%. So it's a little far away from the 18.6%. So let's see. My z-score for 10% is going to be 0.10, so that's my actual proportion, minus the true proportion, the parameter, all over my standard deviation. And that is negative 2.21. I'm going to go ahead and draw a curve and shade in negative 2.21, which is roughly there. So I should get a small probability. And how do I calculate it? Usually, you're going to use your calculator. You're going to go second distribution, normal CDF. For the lower, make sure you're going all the way to the left. So negative infinity is great. All right. For your upper, negative 2.21 would be fine. All right. And by the way, on your calculator, since you can't technically key in negative infinity, if it defaults to that negative e to the 99 thing, that's great. Don't worry about it. But if it has a number in there, you just use a really large negative number like negative 100,000 or something. And it should give you a pretty good value for your probability, which is 0.0136. So we should only see in about 1% of the samples, there's only a 1% probability that a sample is going to give us less than 10% with military experience. So the other thing, what we really love to do with proportions is to compare them. And that can be done by looking at the difference of two groups, P1 minus P2. When we studied random variables, we learned we could calculate expected values for combined random variables if they were approximately normally distributed. If two samples meet both the 10% condition and the large counts condition, then we can use the following rules to combine them. So if I'm combining means, let's say I'm saying x1 plus x2, and then I say minus this one, I'm just going to match whatever I do to the means to what's going on in here. So if I add, I add. If I subtract, I subtract. So that's really straightforward. Expected values behave very well. Variance, on the other hand, never subtracts. It only adds. So if I have multiple variables I'm combining, even if I'm taking the difference here, I'm going to be adding those variances. And remember that variances are just standard deviation squared. And if I want to get back to the combined standard deviation, I have to take the square root. Okay, so let's go ahead and apply that to the difference of two proportions. Oops, let me go back. Again, remember, variances always add. So for the difference of two proportions, we're going to say x1 is really p1, or p hat 1, and x2 is p hat 2. We only have two samples. We're subtracting. So it's just going to be p1 minus p2, because the expected value for x1 is p1, and for x2 is p2. Variances we're going to add. So we're going to add the variance for p1 and p2. By the way, that's just the standard deviation squared for P1 and the standard deviation squared for P2. Well, I can substitute in, because it's a proportion, I know what the standard deviation should be. So for sample 1, it should be whatever P1 is, times 1 minus P1 all over N1, take the square root, but I'm squaring it. And then the same thing for sample 2. So if I square it, that essentially gets rid of the square roots, and I have that. Then to get the standard deviation from the variance, we take the square root of that, and that gives us our formula. Okay, so what about conditions when you're doing two samples? Well, each sample needs to meet the 10% condition, so values for the standard deviations are accurate if sampling without replacement, which is almost always. If both N1 is less than 10% of the first population, and the second sample is less than 10% of the second population, and randomization is used, we can assume independence within each sample. Now, each sample also needs to meet the large counts condition so that the sampling distribution for each proportion can be assumed to be approximately normal. In addition, both samples need to be independent of each other so that we can add their variances. So let's go ahead and look at AP exams again. Now we're going to do a slightly different context. A random sample of 90 AP exams administered by School A showed that 71 had passing scores of 3 or higher. A random sample of 100 AP exams administered by School B showed that 75 passed by scoring 3 or higher. School A administers 1,195 AP exams, and School B administered 1,204 AP exams. So we're going to let proportion of A minus proportion of B be the difference in the sample proportions of passing exams. So what is the shape of the sampling distribution for the difference and why? Well, we can say it's approximately normal because the large counts condition is met. And the sample size A times proportion for A is 71. Now, you're probably going, wait a second. You don't know proportion A. Well, I could go back and calculate it, but remember, it's just the expected number of successes. So I can cheat and just say, oh, 71 succeeded. And then for the failures, oh, it's everybody else. So it's 19. Same thing for School B. All right. All these numbers are greater than or equal to 10, so we can say it's approximately normal. Now we're going to find and interpret the mean of the sampling distribution. So now I'm actually going to go ahead and calculate the proportions. So it's 71 out of 90 minus 75 out of 100, or 0.7888. It's really repeating. Maybe I should have put a 9 in there. Minus 0.75, so it's 0.0388. All right, so that's the mean. So the proportion of students passing the AP exam at School A is estimated to be 0.0388 higher than the proportion at School B. And I like saying it's estimated because I actually don't know the true value, but that's we're hoping it's close to the true value. So then we want to calculate and interpret the standard deviation of the sampling distribution. And we need to verify our 10% condition. So first, let's go ahead and calculate it. We'll substitute in our values, and we end up with the standard deviation of 0.0610. Now, let me check my 10% condition. And 90 is definitely less than 10% of 1195. It'd have to be like, as long as it's under like 120, we're good. And 75 is less than 10% of 1204. Also, as long as we keep it under 120, we're fine. Okay. So the difference in proportions of students passing at School A and School B typically varies by about 0.0610 from the true difference in proportions of 0.0388. So, well, I would probably say the estimated difference because technically we haven't measured everything. So I'm a little leery of saying true. True tends to apply to the entire population. Okay. Estimate the probability that the proportion of passed exams at School A is higher than the proportion of passed exams at School B. So remember, we found these two in the last bit, and we're trying to find this. And you're probably going, wait a second. How do I calculate a z-score for that? I've got two different proportions. Well, if we make it look like this, we're in not such bad shape. So we're going to subtract this from both sides, and we end up with this. So my z-score, if this difference is greater than 0, then School A had a higher proportion of passing exams. So I'm going to use, for my z-score, 0 minus the difference, the estimated difference, all right, over the standard deviation. And I get a z-score of negative 0.636, which leads to this picture. Now, it really helps to shade it in and know which way you're going because you could have easily assumed it was to the left. So I always like shading it in and knowing what I'm doing here. So that tells me that this is the lower boundary for my normal CDF, z lower, and that z upper is positive infinity. Again, since you can't normally enter infinity, put something like 100,000 or something in. So finally, using either a calculator or a table, you determine that the probability that school A has a higher proportion passing than school B is almost 73.76%. So 3/4 of the time almost, school A is going to have a higher proportion than school B in samples we take. At least that's our estimate.